This is the 40th lecture of the course on ground improvement and geosynthetics, and in fact, I am very happy that I will be talking about a new topic today, nanotechnologies in ground improvement and site remediation. We are all aware that the nanotechnologies have made a significant difference, and people have been talking about the use of these technologies in many areas of science and engineering, and definitely ground improvement is not an exception. So, I would be trying to cover some introduction, the science and technology of the nanotechnology, the applications, particularly some geotechnical considerations, and also how it can be very useful in ground improvement, and what are the research needs and what are the implications. This technology of nanos are the finest materials, have the finite materials in that sense, has been initiated when Richard Feynman, a professor at Caltech, introduced this to this world, the concept of nanotechnology, where he talked about the plenty of room at the bottom. And we are all aware that nanotechnology is an emerging field, and it is an interdisciplinary field where it has a lot of potential for interdisciplinary and cross sectoral applications. In some cases, it deals with understanding and control of the matter at the finest dimensions, roughly of the order of 100 nanometers and below. And if you look at commercial aspects, major industries like materials, manufacturing, and composites of products are taken a big lead in this. Even electronics, particularly the nanoelectronics, has been a well received area. Healthcare and life sciences are also some more applications. And nanometer is nothing but a 1000 millionth of a meter. So, if you want to understand what it means, a human hair is about 80,000 nanometers wide, a red blood cell is about 7,000 nanometers wide, and a DNA molecule is about 2 to 2.5 nanometers, and the water molecule is about 0.3 nanometers. So, you can see that whatever dimension that we are thinking about, particularly at the finest for the very fine scales, one can express in terms of the nanos, and the way that it works is that it is a technology for making things by placing atoms precisely where they are supposed to go. By organizing individual atoms and molecules into a particular configurations, these molecular machines are able to create works of astonishing complexity in size, such as human brain, a coral reef, or a redwood tree. You can really create something different or something same or new or whatever. So, nature shows that molecules can serve as machines because living things work by means of such machinery. Enzymes are molecular machines that make, break, and rearrange the bonds holding other molecules together. So, the key to application of the nanotechnology will be the development of processes that control placement of the individual atoms to form products of great complexity at extremely small scale. What nanotechnology can do? A full-fledged nanotechnology promises nothing less than complete control over the physical structure of the matter. This is something astonishing and amazing. Known as assemblers, these tiny devices would be capable of manipulating individual molecules very rapidly and precisely. According to a programmed set of instructions, a nanotechnological approach would be to produce substances that conventional biotechnology could not. After performing the task, these devices may be induced to self-destruct or remain in surveillance mode, or in some cases integrate themselves to the body cells. Such devices would have dramatic implications for the practice of medicine and for the society as a whole. The applications of nanotechnology, the automotive industry will be certainly influenced by the development and implementation of nanotechnology. Due to small size of the nanomaterials, their physical chemical properties like stability, hardness, conductivity, reactivity, optical sensitivity, melting point, etc., can be manipulated to improve the overall properties of the conventional materials. Coolants utilize nanoparticles and nanopowders to increase the efficiency of the heat transfer and potentially reduce the size of the automotive cooling equipment. Nanoparticles of metals are being considered for potential use in catalytic converters, since the catalytic reactivity would be significantly enhanced due to the increased surface area of the metal. Some manufacturers are currently using nanomagnetic fluids in shock absorbers to increase the vibration control efficiency. Water resistant hard surface nanocoatings are being investigated for applications in bearings, cylinders, valves and other highly stressed components. High efficiency nanolayers of semiconducting materials provide electronic components and systems with a long lifetime. Sensors are being used and they are based on nano layer structures, finding applications in engine control, airbags, anti-lock brake and electronic stability program systems. Nanoparticles may also assist in the optimization of conventional components like batteries, catalysts, solar cells or fuel cells. So, when it comes to civil engineering, they have been useful in concrete. There is some research that is being done. Addition of nanoscale materials to cement could improve its performance. For example, Lee found that nano SiO2 could significantly increase the compressive strength of concrete containing large volume of fly ash at an early stage and improve pore distribution by filling the pores between the large fly ash and cement particles at nanoscale. It has been reported that adding a small amount of carbon nanotube by weight, say for example 1%, could increase the both compressive and flexure strength. When the nano capsules are broken by a crack, the healing agent is released into the crack and contact with the catalyst. This polymerization happens and they bond the crack faces. So, the self-healing polymer could be essentially applicable to fix the micro cracking in bridge piers and columns, but it requires costly epoxy resin. So, what I would like to say is that the nano materials, say for example, in nano SiO2 could definitely increase the strength of the concrete, stiffness of the concrete. It can be used for crack healing as well where it is required. And when you try to think of steel, there is a material called Sandvik NanoFlex TM, which is something a new stainless steel material with ultra high strength, good formability and a good surface finish developed by Sandvik NanoFlex materials technology. It is suitable for application which requires lightweight and rigid designs. It has good corrosion and wear resistance and can keep life cycle costs low. Alternatively, wear resistant surfaces can be achieved by various treatments. So, what do we do in geotechnical engineering? This is a very interesting to observe that in geotechnical engineering or even in soil scientists, though they themselves do not call them as nanotechnologies, people were trying to study the clay size particles of less than 0.002 mm, and this has been there for more than 30-40 years, and they are among the earliest workers in the field of nanotechnology. So, that way I must say that geotechnical engineering has started the area of nanotechnology quite long back, whereas others could do it in the recent times. Most material types and properties change with scale. In geotechnical engineering, for example, soil particles change in composition shape from predominantly bulky quartz and feldspar to platy, mica and clay over a range of particle sizes from sand and gravel down to silt and clay. So, the challenge in geotechnical engineering is to understand the changes in properties and behavior in moving from large to small, whereas the central theme in nanotechnology is to take advantage of this transition and attain novel material performance through nanostructuring of new materials. So, there is an interesting difference here that you are trying to manipulate the structure of the materials and by using this nano particles, and so for this one needs to understand the various particle sizes that are available in nature in soils. the challenge, as I just mentioned, is to what you see observe in nano level needs to be upgraded to processes and physical phenomena that occur at macro scale, behavior and materials and structures that are usually the endpoints in the engineering efforts. So, the fundamental behavior of clays is a nanomechanics problem, as I just mentioned, suggesting that the concepts and models developed in nanotechnology can provide new insights and enhanced understanding of the behavior of clay sized particles, and even more importantly new means to manipulate or modify the behavior. You can see that here that 1 micrometers and less than 100 nanometers, if you take, definitely you have materials like Montmorillites, olefins, halocides, organic molecules, and some of them are already there. So, these people have been using in geotechnical engineering practice, particularly in the area of geo-environmental engineering, to modify the soil properties. Soil and rock are the most abundant and lowest cost construction materials, and in some states like dry, dense and cohesive states they are strong and durable. In other cases, loose, wet and soft, they are weak and unusable or unsuitable. It is possible or even conceivable that the new knowledge and the development of process at the nanoscale may someday transform these materials in ways that can make them even more useful and economical. Developments in nanotechnology can aid in understanding the fundamental behavior of the fine grained soil at the particle level and lead to the development of engineered fine grained soils. Readily available atomic force microscopes are now being used in mineral studies to explore local mineral variations in clays, such as surface charges and local hydrophobicity on mineral surfaces. And nanoparticles might also be engineered to act as functional nanosensors and devices that can be extensively mixed in soil or used as smart tracers for the in situ chemical analysis, characterization of groundwater flow and determination of fracture connectivity, among other field applications. There is a small example in literature in one of the case studies from in literature, and they have just taken two types of soil. One is a normal soil, one is a nano soil. Nano soil is nothing but a product of milling of the natural soil with a greater portion of its particles are pulverized into nano sizes 1 to 100 nanometers. Additives are added to soft clays and peat for stabilization because construction is impossible with the soils. So, the two criteria should be satisfied to any candidate material for soil improvement. One, it should be non-toxic and also inexpensive, and nano soil satisfies both. And in one of these papers it is indicated that the liquid limits, plastic limit and plasticity. If you add liquid limit increases, definitely it is about known well that they are much more finer particles. So, the surface area increases, so liquid limit increases, plasticity also increases, but on the other hand plasticity index, which is the difference between liquid limit minus plastic limit, decreases, and specific surface also you can see that it increases and compressive strength also increases. That is an important point. Like you have a kaolin clay which is original specific surface 25.3 meter square per gram. After milling it has increased to 39.8, and for example original Montmorillite it is about 730 milli square meters per gram. After milling the same increases to 792, and if you add the original soil, for example you have taken a original soil, it is about 2.4, after milling it has become increased to 3.9. Now when you look at the impact of this nanoparticle addition to the soil, you can see that the average compressive strength is in the range of 689 kilonewton per meter square when there is no nano soil, but then if it is 1% it is increased to 1149, and then with 2% it is increased to 1493. So, what it shows is that a small study, the small addition of the nanoparticles show a marked increase in strength response, And reduction in plasticity index is another important useful contribution, and because we expect that less plasticity means less problem. So, strength of the soil cement mixture almost doubled when 1% nano soil was added, and additionally soil with cement and nano soil will have lower tendency for volume change and plasticity index in addition to increasing load carrying capacity. So, this is a useful thing, but as I just mentioned, this area of nanoscience and technology has been being pursued in more in the area of site remediation because of the impact it has. Because many countries have a lot of contaminated sites which need to be cleaned up, and in the past 10 years emerging technologies such as phytoremediation, bioremediation, permeable reactive barriers have become popular new tools. These novel treatments have begun to compete with more established technologies such as solidification, stabilization, vapor extraction and all that. And of course, forefront of these methods emerging technologies is the development of nanotechnology for site remediation. One emerging nanotechnology, nano-sized zero-valent iron and its derivatives has reached the commercial market for field scale remediation studies. I will give a small background in this. Over the years, the field of remediation has grown and evolved, continuously developing and adopting new technologies in attempts to improve the remediation process. In the 1990s, the reducing capabilities of metallic substances such as zero-valent iron ZVI began to be examined for their ability to treat a wide range of contaminants in hazardous waste water. The most common deployment of ZVI, zero-valent iron, has been in the form of permeable reactive barriers (PRBs) designed to intercept plumes into the surface and subsequently remediate them. The first full-scale commercial PRB was approved for use in the state of California by the San Francisco Regional Water Quality Control Board, and the way that the technology works is that nano size zero-valent iron and the reactive nanoscale iron product comprise the most basic form of the nano iron technology. Particles of NZVI may range from 10 to 100 nanometers in diameters of slightly larger, and figure 1 shows the transmission of electron microscope images that I will show. The most common route to NZVI synthesis employs sodium borohydride as a key reductant. So, by mixing sodium borohydride with this FeCl3 6H2O and iron ferric ferric ions are reduced according to the reaction that we have here in this form. And you can see in this figure that the way that the images are there, and following this reaction the reduced particles of iron created could be directly used for contaminate destruction. So, you have stoichiometry of the reduction of the TCE trichloroethane to ethane. A typical decontamination reaction would proceed. This is a chemical reaction that we have, and a recent study by Liu et al. Compared the efficiency and degradation capabilities of NZVI synthesized using sodium borohydride reduction and the RNIP particles produced from ferrous sulfate. It was concluded though that the presence of boron and the shell thickness were the most likely explanations for observed differences in reactivity. The NZVI particles demonstrated rapid dechlorination of the TCE and no deactivation. However, rapid H2 evolution was observed. So, other methods of producing nano-sized iron particles also have been developed. Ball milling represents another technique. In this process, micron size iron powder is reduced to nanoscale through an attrition or abrasion using a ball mill. That is what I gave an example just now, how a milled material can increase the strength of the soil. A vacuum or a gas condensation process has also been used to produce nano-sized iron and other materials or metals. As with the addition of metal catalyst to NZVI particles, the formation of emulsified zero valent ion also represents an enhancement to the existing NZVI technology. So, the applications, the remedial application is that the small size particle size and high specific areas to mass ratio make iron nanoparticles highly reactive and extremely versatile. The high surface area and surface activity compared with the granular forms enable the nanoparticles to remediate more material at higher rates and with a lower generation of hazardous products. The ability of the nanoparticles to act as strong reducers also enables the remediation of an extremely wide range of contaminants. So, the table 1 which I will show now has that what are the contaminants that can be remediated by nanoscale iron. You have a number of contaminants here, carbon tetrachloride, chloroform and DDT, orange there are many things, mercury, nickel, silver, cadmium, all of these contaminants, PCBs, TNTs, all that. You have a whole range of applications here. So, in conjunction with nano iron's device group of target contaminants, the field scale of net deployment of the particles can be achieved by varieties of ways. Nanoparticles were mixed with water to form a slurry that can be injected using pressure or gravity into a contaminated plume. Once injected, the particles remain in suspension, forming a treatment zone. Particles of iron can also be used as ex situ slurry reactors to treat soil, sediment and solid waste. The injection of the nano iron into the ground represents the most common deployment of this technology thus far, like this. Okay, injection well you have, and if there is a contamination flume, you can have a barrier, reactive barrier like this. Overall, the process provides a number of remedial benefits. Most importantly, the technique facilitates source zone remediation, which is a very important, a clear benefit in the case of site cleanup. A few case studies here. In the case studies of the fate and transport of nanoparticles for site remediation, it is in manufacturing plant Trenton, New Jersey. This manufacturing plant synthesizes bimetallic particles. In order to achieve the bimetallic catalytic effect, iron and palladium are combined in the ratio of weight ratio of 1:300. The reactive catalyst coating is applied via the following reaction. You have a reaction here. BNP material is introduced to the contaminated groundwater plume via injection wells, and the reactive agent is distributed throughout the target area via simple suspension groundwater. Monitoring at the piezometer suggests a significant discrepancy in migrant states of the plumes after the BNP injection. A patented BNP based project known as Nano Fe plus TM, developed by one company, Pars International, is used for remediation at the Klockner road site. Pars Environmental Inc. reports that the reactive agent is administered in a water based slurry containing 1 pound of reactive material in each about 4 gallons of solution. Currently, little information is available on the fate and transport of the Nano Fe plus particles in the subsurface at the site. The injection phases and quantities of injections are known, and 2 monitoring sessions are scheduled to take place after the 2 injection phases. So, monitoring will be conducted to determine the amount of dense non-aqueous phase liquid reduced by nanoscale iron. So, efforts are being done on this, but nevertheless one should understand that yes, it has been attempted in the field, and there is a case study available. To understand, maybe one should just take the update from the company itself on what is going to happen, what is happening at the site. The other one was the NASA launch complex in the Florida, Cape Canaveral. The site is well known for its historical use. Typically with the use of rocket fuel, the chlorinated compounds such as TC, this is a contaminant, exists in the site's groundwater, soil and sediment. So, 3 methods of administering NZVI will be field tested at the large complex as alternatives to the direct injection method. One is a pressure pulsing. The pressure pulsing involves forced administration of NZVI particles to various and relatively predictable subsurface depths. Pneumatic fracturing employs compressed air to create subsurface crevices and small pathways that facilitate distribution of the reactive medium. So, another one is the hydraulic fracturing. In a way similar to pneumatic fracturing, hydraulic fracturing uses high pressure liquids to enhance reagent distribution in the subsurface. Typical changes in concentration reductions in the area of NZVI are shown in the figures, like you can see that there is some concentrations here. NaPl is injected. After 2 weeks after injection, you can see that green line indicates it is little better, like you can see in the previous site. It is much lesser. So, I mean, we can only understand that there is some, so the green zone has increased. With the result, what it means is that this from an ESCPA study that this technique has been effective. So, what it means is that these case studies indicate that NZVI based technology has potential as a means of remediation. When accompanied by sound environmental safeguarding, the technology may prove to be safe and reliable. And this remediation technology developers need to recognize that the release of the synthesized materials with complex multi-molecular nanoscale structures will generate questions concerning potential ecological and environmental threats. Of course, small is very small is fine, but if it is going to cause bigger damages, also one should be careful. Based on the information available, the current methods of nanoscale ceramic do not appear to pose a threat to humans and the environment. There is some assurance available here. One of the limitations, some of the limitations you should be able to understand that site specific conditions such as site location, layout and geological conditions, concentration of contaminants and types of contaminants may limit the effectiveness of nanoparticles. The research conducted for the 2 sites that have used nanoparticles in fractured bedrock, although several pilot studies have been undertaken. Prior to injection of the nanoparticles, geological, hydrogeological and subsurface conditions should be evaluated to determine whether injected particles would have adequate surface infiltration. Factors that affect surface mobility include composition of the soil matrix, ionic strength of the groundwater, hydraulic properties of the aquifer, depth to the water table and geochemical properties. Studies have shown that the nanoparticles may not achieve widespread distribution in the subsurface due to the agglomeration prior to complete dispersion within the soil or groundwater makes, limiting the radius of influence. What are the research needs? So, of course, this area, I know there is a beginning in this area, but then we need to understand what can be done. So, to assess the extent to which nanotechnology applications reach soil and water systems beyond immediate application areas, one needs to really have a far sight ahead in this area. Evaluate the potential impact of the nanoparticles of specific and immediate environmental media. Determine whether and the degree to which nanoparticles may travel through the food chain. Preliminary research already indicates that some nanoparticles may be taken up by bacteria in trace amounts. That is one thing one should see. Examine the uptake of nanoparticles in the animal species. When it comes to cost, yes, factors contributing to the cost include the site type of contaminants, concentrations of contaminants and the challenges that may occur during remediation. Additional factors that may increase the total cost of the nanoparticles application may include operational requirements connected with any contamination found underneath a building or the need to treat or dispose the extracted fluids. I know that nanoparticles are available in many places, and we need to really handle them in a way that lot of science behind that, and its reactions with soil need to be understood before we go for some more broad conclusions in this area. And we have a lot of contaminated soils. We should be able to work and see if nanoparticles can be effective and establish some sort of understanding there. What is happening in India? One should understand that nanotechnology in India is a government led initiative. In Indian Institute of Science, there is a big interdisciplinary center in the area of nanoscience and engineering, which is quite a big center, and which is support from the government. And industry participation is very recently originated, and industry is also moving towards that. Enabling energy storage, production and conversion with the renewable energy frameworks is also there. Enhancement of agriculture productivity through pesticides. Yes, nanoparticles, can it lead to agricultural productivity increase? Nanotechnology is slowly implemented being implemented in medical field, textile industry. Sectors such as health, energy and environment have received greater attention by various technology departments. In fact, Department of Science and Technology is looking at very seriously, Department of Biotechnology and SCRC. They are all looking at nanotechnology with lot of curiosity, and they are looking at the implications. They hope that definitely if nanoscience can bring in a lot of change, whether it is in the agriculture production or in trying to remediate contaminated sites, it is going to be wonderful, because or even health and energy and other issues. So, so I must say that when you have this technology, people should understand that the field implementation is not simple, because in terms of the nano fabrication, other branches in mechanical engineering and electronics engineering, it is difficult, but in the area of geotechnical engineering, implementation in the field is not easy, because it depends on the site conditions, but nanotechnology promises as a safe and fast remediation technique or a process. When accompanied by sound environmental safeguarding, the nanotechnology may prove to be safe and reliable. I am sure about it, and nanotechnological approaches would be able to produce substances that conventional biotechnology could not. So, definitely this technique facilitates source zone remediation, a clear benefit for the site cleanup, and I am sure that the references that I have indicated here, particularly from Wilson and Zhang, and also some of these references are quite useful. And actually in this preparation, I must thank my students, Mr. Manohar and Abhinay, for help in the preparation of this material, and also say that it has been quite a successful one. With this, I would like to conclude this lecture, 40th lecture in this series, in this course, and I would like to thank NPTEL, who have been the force behind this particular initiative at the Government of India level, and their constant encouragement towards this course has helped me a lot in reaching this deadline, and the staff of the NPTEL here in Institute of Science have been of great help in trying to organize these lectures. The institute has been of considerable help, and students of my classes who took this ground improvement course, and they have been quite helpful in the whole in participating in discussions and in preparation of material various times. And there are a number of people from industry, particularly in the area of ground improvement. You need to interact with industry, and many of them they supplied with their material and to be shown, because ground improvement techniques need a lot of case studies, and you have a lot of support from many companies, say for example Keller, and there also I use some material from internet as well. Some materials here and there have been used, and I must thank all of them who have been very helpful in both in direct way and indirectly in the development of this course. So, I thank you again, and I will be very happy to provide or improve this course further with inputs from everybody. Thanks again, one and all. Bye.